So 5.4. All right, so these formulas, these are ones where I'm going to give you the formulas. You on these, you'll just have to, where you're just going to have to take my word for them on these. We're not going to go through all where they all come from. It's showing where they come from kind of geometrically with the triangles and the sides of triangles. Not difficult, but it's a little bit tedious. If you're interested, I think they do them in the back of the chapter 5 in the book. So basically you're going to have to take my word for these and just remember how they work. So we're going to talk about, what I want to do is just list our formulas and then do some examples of the kinds of problems that you would see with these formulas. So the sine of u plus v. Unfortunately, and I try to write my v's with little tails on them because my u's and v's tend to start looking the same. Unfortunately, it's a little more complicated than sine u plus sine v. So our formula, sine u cosine v plus cosine u sine v. So that's our sum formula. The sine of u minus v equals sine u cosine v minus cosine u sine v. And what I remember with these is that the signs, the plus or the minus, is the same, and the sines and cosines are always mixed. Cosine of u plus v, cosine u cosine v minus sine u sine v. And then our difference formula, cosine u cosine v plus sine u sine v. Yes? This one? So with cosine, the plus and the minus in our formulas changes. So in sines, if this is a plus, this is a plus. The cosines, if this is a plus, that's a minus. And I remember that the cosines and the sines are always together, and then the plus or the minus is opposite. These four, I would ask you to remember. The sine function, the sine identities and the cosine identities are the same, other than the positive and negative sign. So with the sine identities, the signs are the same, the plus and minus are the same, cosine they're opposite. The sine identities, the sines and cosines are mixed together. With the cosines are together and the sines are together. All right, and then the tangent formulas, the sum and difference formulas for tangents, I would give you. I'll write those on the board for the test. So the tangent, because they're a little more complicated. Tangent of u plus v equals tangent u plus tangent v over 1 minus tangent u tangent v. And the tangent u minus v, tangent u minus tangent v over 1 plus tangent u tangent. So these I would write on, these two I would write on the board for the test. The reason that we use these or where they come up is often it is easier to work with this formula than with this formula. And often when we write the sum or the difference in this form rather than this form, we can get some things to cancel out and simplify equations when they involve a sum or a difference of an angle. so they can simplify, and they also let us write functions or find sines and cosines of angles that are not on the unit circle angle, but that are related to unit circle angles. And those are some of the examples that we're doing. And I'm just going to write one of these. So remember, for all these, sine of u plus v, I'm just going to use sine does not equal sine u plus sine v. So don't make that mistake. It's more complicated than this, unfortunately. All right, so let's. What I want to do next is just go through some examples of how we are going to use these formulas, and what kinds of questions you might be asked that involve these formulas. All right, we good? Okay. So first one, find the exact value of the sine of 15 degrees. So the fact that we have the question says exact value tells us we're not plugging this into our calculator. This somehow involves unit circle angles. So what we have to do here is we want two unit circle angles that add or subtract to 15 degrees. So what would two unit circle angles that add or subtract to 15 degrees? What is it, Josh? 45 and 60. So 60 minus 45 degrees equals 15 degrees. The first one I thought of was 45 degrees minus 30 degrees. Either one of these is going to give us the same answer. So let's go with Josh's suggestion. Now is this, so we're finding the sine of 60 degrees minus 45 degrees. That's 15 degrees. And we just talked about a formula for the sine of u minus v. So we plug this into our formula. So this is going to be the sine of 60 times the cosine of 45 degrees minus the sine of 45 degrees. Well, let's write it the way that we wrote it. Cosine of 60. So I'm writing it in the same order that we wrote in our formulas. Sine of 45 degrees. And we can find these on our unit circle. So the sine of 60 degrees is 1/2. Cosine of 45 is square root of 2 over 2. Minus the cosine of 60 is square root of 3 over 2. Sine of 45 is 1/2. So this equals square root of 2 or sorry, not 1/2, square root of 2 over 2. Square root of 2 over 4 minus the square root of 6 over 4. And I could write that as square root of 2 minus the square root of 6 over 4. Did we get these switched around? Sine of 60 is square root of 3 over 2. And cosine of 60 is 1/2. So this should be a square root of 6, and that should be a square root of So the exact value of the sine of 15 degrees is square root of 6 minus square root of 2 over 4. We can multiply under the square root, just as a reminder, multiply, but we can't add or subtract. So we have to leave these two written separately. All right, so that's one way that we would use this sum and difference formula. Let's just write the sine of the exact value sine of 15 degrees. All right, let's look at one of these using radians. Questions on the process there? Okay. We want the exact value of the cosine of 7 pi over 12. So this exact value tells us that it has to do with unit circle angles, and we want two angles, unit circle angles, that add or subtract to 7 pi over 12. Any ideas there? All right, so when we find a common denominator, when we find this common denominator of 12, all of our unit circle angles have some kind of fraction. And when we find a common denominator, we're multiplying one fraction by the denominator, the denominator over the denominator of one side and the denominator over the denominator of the other side. So essentially what we're looking for here is two numbers that multiply to 12 and add to 7. So what would that be? We only have certain fractions on the unit circle, right? We have 2, 3, and 4. Pi over 2, pi over 3, pi over 4. So pi over 3 and pi over 4. So pi over 3 plus pi over 4 equals 7 pi over 12. Because to find my common denominator here, I multiply this by 4 over 4, and multiply this by 3 over 3. So my common denominator is 12, and I add the 4 and the 3 to get the 7. So what we're looking for here is the cosine of pi over 3 plus pi over 4, and we have a nice formula for the cosine, a sum formula for cosine. So that's going to be cosine pi over 3, cosine pi over 4, and the signs are opposite, minus sine pi over 3, sine pi over 4, and the cosine of pi over 3 1/2, cosine of pi over 4 square root of 2 over 2, minus sine of pi over 3 is square root of 3 over 2 times the square root of 2 over 2. So we get the square root of 2 over 4 minus the square root of 6 over 4. And that gives us the exact value of the cosine of 7 pi over 12. Questions there? Okay, let's look at one of these in reverse. We want the exact value of the cosine of 78 degrees times the cosine of 18 degrees. Thank you. Plus the sine of 78 degrees times the sine of 18 degrees. So what we want to do with problems like this is match the form of the problem to an identity. So what identity has a cosine and a cosine and a plus and a sine and a sine? Yes. Cosine u minus v. This matches the form of cosine u minus v. So this is going to be the cosine of 78 minus 18, which is the cosine of 60. And the cosine of 60 degrees is 1/2. So that whole thing simplifies to 1/2. So on this kind of problem, we want to match the form of the problem to one of our identities. All right, questions on that example? All right, here's one of our favorites, and we're ready to, now we know how to verify this. We want to verify our favorite cofunction identity, sine of 90 degrees minus x equals cosine x. We have the tools now to do this. This is the sum, this is the difference of two angles. So we can use our difference formula. This is the sine of 90 degrees times the cosine of x minus the cosine of 90 degrees times the sine of x, using the difference formula for sine. Sine of 90 degrees is 1 times the cosine of x minus the cosine of 90 degrees, 0 times the sine of x, and we get cosine of x. Yes. So this one not asks us to verify it. So this is how we verify, how we show that it's true. We kind of already know, but this is just show how we can use these formulas to get to the same place. All right, questions on that one? All right, let's look at a tangent, one of the ones for tangent. We want the exact value. Of tangent 255 degrees. So again, we want two unit circle angles that add or subtract to give us 255 degrees. The first ones I thought of were 300 degrees minus 45 degrees. There are other pairs that work also. All of them will lead you to the same answer. So these are just the two that I thought of, the first two that I thought of. Yes? Because we don't know the tangent. We don't know the tangent of 255 degrees. So in our formula, we have the tangent of u and the tangent of v. We would, to find the exact value, then we would have to know the exact value of tangent 255. All right. So tangent of 255 degrees equals a tangent for the pair I chose, 300 degrees minus 45 degrees. And we plug that into our tangent difference formula. So this is going to be the tangent of 300 minus the tangent of 45 over 1 plus the tangent of 300 times the tangent of 45. And I plug these in. Tangent of 300, we can find these on our unit circle, is negative square root of 3 minus 1 over 1 plus negative square root of 3 times 1. and I get, I'll just rewrite this in kind of a bit more standard form. Negative 1 minus square root of 3, and 1 minus square root of 3. And I would not ask you to rationalize this one. If you left it written like this, that would be fine. And we can't cancel anything out here because there are no common terms. We can't cancel these square roots of 3 because it's not common to both terms. So we just leave it written like that. And that's our exact value of the tangent of 255 degrees. All right, questions there? Okay, I've got two more examples that I want to go through. We'll use our identities to solve cosine x plus pi over 4 minus the cosine of x minus pi over 4 equals 1. So the way that we solved equations before, we really couldn't do anything with this. But now we have our sum and difference formulas. We can use our cosine sum formula here and our cosine difference formula here and see if that leads us anywhere. So I'm going to plug this into my sum formula for cosine here. This is the cosine of x times the cosine of pi over 4 minus the sine of x sine pi over 4 minus, and I'm going to put parentheses because this is a big expression, cosine of x cosine pi over 4 plus sine x sine pi over 4, and that equals 1. Cosine of pi over 4 is square root of 2 over 2. Square root of 2 over 2 cosine x minus sine of pi over 4 is square root of 2 over 2. Square root of 2 sine x minus square root of 2 over 2 cosine x minus square root of 2 over 2 sine x equals 1. And I have a square root of 2 over 2 cosine x minus the square root of 2 over 2 cosine x. So those go away. And I get a minus 2 square root of 2 over 2 sine x. So I get minus square root of 2 minus square root of 2 over 2 minus square root of 2 sine x equals 1. So I have a minus 1/2 minus 1/2 is minus 1. So sine x equals minus 1 over square root of 2 over 2, which is minus square root of 2 over 2. And then we go to our unit circle and say, where is sine, the sine of our angle equal to negative square root of 2 over 2? X equals 5 pi over 4 plus 2n pi, and x equals 7 pi over 4 plus 2n pi. So we went from an equation that we would be able to solve the way we did it before, used our sum and difference formulas, and we were able to come up with a solution. Questions? Yes. So I had a minus from these two. I have a minus square root of 2 over 2 sine x minus square root of 2 over 2 sine x equals 1. I have a minus 1/2 minus 1/2 is minus 2/2, which is just minus 1. Does that make sense? So that leads us to there. All right, one more example. We want the exact value of cosine of u minus v if sine u equals 5/13, cosine v equals -3/5, and u and v both in quadrant 2. All right, so we want cosine of u minus v. We have sine u and we have cosine v. This should be -3/5. What are we missing for our formula for cosine u minus v? I have sine u and I have cosine v. What else do I need? Don't I need cosine u and sine v? If sine u is 5/13, how do I find cosine u? Draw a triangle. This tells me two sides of a right triangle. I can draw a triangle, find the missing side, and find cosine u. Very good. And if I know cosine v is -3/5, how do I find sine v? Draw a triangle, find the missing side, use the Pythagorean Theorem, and then you can find the cosine of, or the sine of that angle. So we need to draw two triangles. So here's my V triangle. There's my angle V. The cosine is, and I need to draw it in the second quadrant, so I need to turn it around. There's V. The cosine is -3 and the hypotenuse is 5. So this missing side is going to be 4 by the Pythagorean Theorem. So I get the sine of V equals 4/5. And for the other triangle, this is my triangle for U. The sine is 5/13. And this is also a Pythagorean triple. This is -12. So the cosine of U is -12/13. And now I have all my pieces. For my formula, the cosine of U minus V equals cosine U, cosine V. So I get -12/13 times -3/5 plus sine U sine V, 5/13. Sine V is 4/5. And I get 36 65ths plus 20 65ths equals 56 65ths. So for problems like these, I have to draw one triangle for each angle that I need to find. All right, questions there? Yes.
Why was it cosine U and sine U?
Cosine U and sine, why weren't they?
Yeah, like the other problem, like cosine, it would be like cosine 90 and then sine.
So this is, so we had, in our formula, this is cosine U, cosine V, sine U, sine V. I'm not sure, so which example were you talking about?
Like on the other ones, it was like that, it was like sine 60 times cosine 45 minus cosine 60 sine 45. Like, why are the sine and cosine?
Is that which example was that one? That one. So because that one was the sine difference formula. On the last example, we're using the cosine difference formula. So here, we have the sine and the cosine; they're mixed. But with the cosine formula, we have the cosines together and the sines together. So let's go back to the very beginning there, Declan. So for the sine formulas, we have the sines and cosines mixed in each term, and the cosine formulas, we have the cosines together and the sines together. I think that's the difference you're seeing. All right. Homework. All right, there you go.